J'ai vérifié la connexion avec Anastasia hier, peut-être.
Oui, hier on a essayé, ça a bien marché.
Très bien. Normalement, ça doit marcher aujourd'hui aussi.
Ouais. Et donc, si je reviens sur...
Bon, let us switch to English.
Yes.
Well, we can wait a couple of minutes, but you can already show
Okay,
your but you can already show your slides.
Right. Okay, do you see my slides?
Yeah, yes, it's okay. We see your slides, yes.
Oh, it is not the good.
Ah, it's not, okay.
Okay. Okay. Okay, this is the good one.
Okay, good.
Yes.
So this is a good one?
Yes.
Okay, then.
The last one was the last that I present when I came in Moscow, but it's a long time ago.
A long time ago, yes. Okay, then we can start, and it's a pleasure for me to introduce our today's speaker, Leon Tine, from France, from the University of Lyon. And Leon will present us his work on the inflammation process in Alzheimer's disease. So please, Leon, you can begin your presentation.
Okay. Hello, everybody. Thank you for coming to this talk. So my name is, as said, Professor Vitali. My name is Leon Matar Tайн, and I'm an associate professor here in Lyon University, and I work in the Institut Camille Jordan laboratory. So, and in real, it is a center of research. We work in mathematics applied to biology. So let me first thanks Professor Vitali for inviting me also, and Anastasia for his help. Okay, thank you very much for this. So my talk will focus on Alzheimer's disease modeling. So here we are looking to the effect of the inflammation in the progression of the disease. And this work is one of the work that we do in Alzheimer's disease, and it is in a collaboration with some colleagues that are here in Lyon University, and the professor Vitaly Verpert, who is here also in Lyon University. And here, my talk will be focused on these different points. So, of course, at the beginning, we will talk about the general context. So the general context here means that we will discuss about Alzheimer's disease, what we know about Alzheimer's disease, of course, in the biological point of view and in the modeling approach. So for this general context, you will see that I will orientate my talk on the one type of modeling of this disease. So after that, I will present you a general model that we design. And for this model, we do some equations that mean we define the model description. And after that, you will see that, of course, we will present some results about this model that mean what is the effect that we find on Alzheimer on the modeling, on the inflammation process on Alzheimer's disease. So after that, we will talk about some numerical simulation to highlight, of course, what we have on the result about the effect of inflammation on the Alzheimer's disease. So, Alzheimer, what is Alzheimer? Alzheimer is a part of the class of neurodegenerative disease that are disabling chronic disease with slow evolution. So these diseases lead generally to a gradual destruction of the functioning of nerve cells, especially neurons, which can lead to death. So the consequences are varied. The consequences can be cognitive, it can be behavioral, sensory, and motors. So what we know is that the guy who discovered Alzheimer's disease is a German neurologist, Alois Alzheimer, in 1906. And the history goes back with the first patient. And it goes back in November 91 with the first patient, call it Auguste Ditti, a 51-year-old woman who suffered from memory problems and language and other physiological disorders. So this is the beginning of this disease. So what happened? What we know in the biological point of view is that there is two types of lesion. The first type of lesion is affected the tau protein. And the tau protein is the protein that maintain, here we have a neuron, it maintains the microtubule of the neuron. So we have here the microtubule are binding by tau protein, and the tau protein maintain this microtubule stable. And it is through this microtubule that there is a nutrient uptake. That means the nutrient come here and access to the heart of the neuron. So when the tau protein are affected, they are here in tangled form, so the microtubule are disordered. So that means the nutrient cannot access to the heart of the neuron. So we have the death of the neuron progressively. So this is the first way of the lesion that are seen in Alzheimer's disease. The second type of lesion is what we call external lesion. The external lesion is due to that what we call Aβ protein. For this external lesion, the Aβ protein is just a transmembrane protein, and I will explain exactly the real process, but what happens is here we have with the Aβ protein we form some like aggregate, and these aggregate are not good for neurons, and this aggregate can also become bigger and bigger, so form what we know about plaque. So in our study we will focus on the external lesion. Okay, For all our study, we focus on the external lesion. We will not talk now about the internal lesion. And for this external lesion, what we know is just at the neighborhood here of the neuron, at the neighborhood of the neuron, as you see here in the first picture, there is something, it is a protein, call it the APP protein. That means amyloid precursor protein. This amyloid precursor protein is a transmembrane protein. And this transmembrane protein is supposed to be coated here by two enzymes. So when it is coated by the two enzymes, it releases what we call beta amyloid. And this beta amyloid is supposed to be dissolved in the neurospinal fluid and to play a nice role for our brain. So of course, it not happen at 100% this case. So that means sometimes the released beta amyloid protein can aggregate all the protein and form what is called beta amyloid plaque. So I will focus on this case to explain you the process. So the process is the transmembrane protein APP, which is here. This transmembrane protein is here. So there is a cleavage of this transmembrane protein. For this cleavage, the normal cleavage is done by two enzymes. That means the alpha secretase and the gamma secretase. When alpha and gamma secretase cut the transmembrane APP, the released part, that means this released part is dissolved in the cerebrospinal fluid, so it will play a nice role for our brain. So of course, there is sometimes the fact that at the place of alpha secretase, there is the beta secretase who cuts. So when there is the association with beta secretase and like gamma secretase, the released part is not at all dissolved in the neuron. It have the ability to aggregate all the protein like here and form what we call oligomers. So the oligomers are not good for the neuron. That's because they are able to send a cytotoxic signal to the neuron and cause its death. So these oligomers are not good for our brain. So, and this oligomer can also, sometimes form what we call plaque. But what we are interested is here, how to understand this process of forming oligomers, A-beta oligomers. Of course, I talk about the normal cleavage and the abnormal cleavage. For this normal cleavage, it is generally, the general case is this normal cleavage. For this normal cleavage, it happens 95% of the case, the APP is cleaved by the two enzymes. That means the alpha secretase and the gamma secretase. And of course, 5% or less than 5%, of course, is done by, the cleavage is done by the beta secretase. That means the association with beta and gamma secretase. And so the released part is not at all dissolved, and so it have the ability to aggregate. That's why it is called A-beta amyloid. Amyloid, that means they have the structure amyloid like the amidon structure to aggregate all the protein, right? So if we come back, it is exactly the scheme that we are now interested is just the 5% that means the abnormal case where we have the cleavage of the APP. It is that the APP, as I said, is a transmembrane protein, and this transmembrane protein, when it is coated by here by beta secretase and gamma secretase, this released part is called beta amyloid. And this released part is just like the number of amino acid, because this is the released part is something like A-beta 44. That means an A-beta protein that contains 42 amino acid. right? If it contains more than 40 amino acid, this related part is not at all dissolved in the cerebrospinal fluid. So this is why this is not dissolved and have the ability to aggregate other protein and at the end form what we call beta amyloid plaque. So what we have now, face it with the aggregation of neuron, because this A beta protein, of course, in its oligomeric form, it sends cytotoxic signal to the neuron, as I said before, and faced to this aggregation, of course, there is an inflammation process appear. This inflammation process appear with the activation of microglia cells. In turn, it produces what we know about the interleukins. So here it is exactly the interleukin, the EL1. So the fundamental question that we ask is to understand the different interaction between A beta protein, microglia cells, interleukins in the context of Alzheimer's disease. So to answer to this question, we designed this scheme. For this scheme, what happened is just we are here in the neuron, and in the neighborhood of the neuron, we have what we call the APP that I said before. That means the amyloid precursor protein. And this amyloid precursor protein, of course, we are in the case of there is the bad secretase that cleave the APP. So when it is cleaved by beta and gamma secretase, it really is like here, A beta monomer in monomeric form. So the released A beta in monomeric form have the ability to aggregate all the monomers, of course. So when two monomers aggregate, they form what we call a proto-oligomers of size 2. And if it aggregate again another oligomers, A beta monomers, so they form a proto-oligomers of size 3, etc. So there is a rate of gain of monomers. So once we have one proto-oligomers, these proto-oligomers can gain monomers and can also release monomers. So the scheme that we have, let me just design it. It's the table that the scheme is that we have is just we have here a population of monomers, and this population of monomers, of course, two of them can merge and form like here a proto-oligomers of size 2. Like 3 of them can also go and form a proto-oligomers of size 3. So what happened is once we have one proto-oligomers of size 2, of course, one proto-oligomers of size 2 can also always gain one monomer and give a proto-oligomer of size 3. Of course, one of size 3 can also we can also lose one monomers and become now a proto-oligomers of size 2 plus one monomers, right? So this is what we call, there is a process of gain and loss of monomers. So here there is a dynamics that form proto-oligomers or come back as monomers. So of course, when I gain monomers, of course, I increase my size, and sometimes I reach a stable size, and this stable size is called oligomers. So this is oligomers, and these oligomers are bad for neuron because they are able to send a cytotoxic signal. Of course, that means when we have the formation of oligomers in the brain, there is an inflammation process because there is something bad for the organism. So there is an inflammation process. So we have the microglia cells are activated. And the microglia cells are activated, and their principal role is just to displace oligomers here in plaque. That means to throw them here in plaque. So of course, when microglia cells are activated, so these microglia cells activate also what we call the interleukins. So we have an inflammatory reaction. So the interleukin are activated, and the role of the interleukin is to boost here the neuron to say that, of course, the neuron are aggressive, so to boost to them to produce A beta like APP, of course. So this is the schematic representation of A beta monomers and inflammation cycle. So now having this model, this scheme, of course, we want to design the model behind. So, of course, before designing the model, when A beta here, A beta oligomers, that means the oligomers is high, where its concentration is high here, of course, there are what we call a phenomenon of stress that call it the UPR, that means unfolded protein response. And this unfolded protein response is due to the fact that, of course, oligomers are here, they send cytotoxic signal to the neuron, and that means they decrease their activity, the activity of the neuron, because the neuron receive a lot of cytotoxic signal. So the decrease of this activity is not good, because in certain time, all the neurons synchronize and, of course, decide to stop their production, their activity. So that is called UPR. And if there is a repetition of UPR in a system, it can call and it can lead to the death of neuron, right? So that's why here we design this kind of model, and we want to know how behaves this system. So let me just note what we said before, is that the role of the microglia cells are responsible to moving the oligomers in the plaque, right? Inflammation seems to play a crucial role in the control of the disease, because we can refer to the work done by Kinnett and al. That call inflammation as a central mechanism in Alzheimer's disease. And this paper was published in 2018. And even in possible research for therapeutic strategies. So when we understand how the inflammation affects the disease, so we can imagine some therapeutic strategy in order to help nurses for this disease, because for this time, of course, we cannot cure this disease. It should, however, be noted the absence of clinical experience. Of course, we cannot cure this disease, so there is the absence of clinical experience for this moment. So, of course, this disease, we cannot treat this disease. That's why, of course, all the studies are good in order to help to elaborate some therapeutical strategy. So if I come back to the scheme that we designed, once you have a scheme, so you put equation on your scheme. So the equation we have is that, of course, we have APP, that means monomers here. So we have the population of monomers, we have the population of proto-oligomers, we have the population of oligomers, we have microglia cells, we have interleukins, of course, we have also plaque. So the first thing is, when we see the dynamic of proto-oligomers, the dynamic of proto-oligomers, the time evolution is follow this equation. This equation mean, of course, the proto-oligomers of size I obtain it when a proto-oligomer of size I-1 gain one monomer. So this is here. A proto-oligomer of size I-1, when it gain one monomer, it become one of size I. So the rate of gain is R I-1. This is a gain term. This term is also a gain term. That means when I have a proto-oligomers of size I+1, when it lose one monomer, it come back to proto-oligomers of size I. That means this also is a gain term. Of course, a gain term. But this gain term is also a lost term when I plus 1 lose 1 monomers. So the rate of losing 1 monomer, we consider it as a constant. That means a B. So after that, of course, when I'm of size I, and when I lose 1 monomer, I become of size I minus 1. That means here we lose it here is when proto-oligomers of size I lose 1 monomers with the rate Ri, right? This is a lost term, and this is another lost term when I lose just 1 monomers. So this is the diffusion term. Of course, we allow the proto-oligomers to diffuse. Okay, this is the first equation. It is the equation, the dynamic of proto-oligomers. Also, we do the same for the monomers. We do the same for all the components of our system. Of course, here, Ri, as I said, is the rate of gain of monomers. So for free oligomers, free oligomers, that means the oligomers that are here that are not yet in the plaque. Okay, for the free oligomers, the things are same. Here, for the free oligomers, what we have for this equation is just, this is the gain term. To become oligomers, it is the last size of proto-oligomers. That means if the biggest size is I naught, so a proto-oligomer of size I naught minus 1, when it gain 1 monomers, it become of size I naught. So it become an oligomer. So the gain term, this is a gain term when a proto-oligomer of size I naught minus 1 lose a monomers. So.
Oui, oh, on a réservé la salle à partir de 16h. Désolé.
Ah, ok, je vais poser. Okay, so I have Vitaly.
Yes, I'm here.
Yeah, okay. You are here. Okay, I have just to move 1 minute.
Yeah,
because,
okay.
all the guys
Go.
just
Yes, go.
okay.
Okay.
Salut.
Désolé, hein.
Non. Sur GRR, j'avais pas vu que c'était réservé, mais hop.
Du coup, je suis plus dans la salle de moi.
Ah, vous êtes, ouais, c'est ça. J'allais y être, mais salut. Ça va? Okay. Okay. Hello, everybody.
Yes, we hear
So
you. We see
okay,
the screen.
I'm very sorry because another team reserve the room, but they do not do it in the platform because we have a platform to reserve the room. So sorry for this. Of course, okay. Let me come back to what I said before. He's here when for the free oligomers, that mean oligomers that are not in the plaque at all. So the formation of these free oligomers depend on just proto-oligomers of size I0 minus 1. When they gain 1 monomer, they become proto-oligomers. Also, here we have the loss of monomer because the microglia cells take oligomers and put them at the plaque. So this is the displacement term with the rate gamma. Gamma is the rate of recruitment, and this rate of recruitment, of course, depends on microglia cells. That's why here we have gamma depending on M. And the dependence of M of gamma is just through a Michaelis-Menten function, right? So this is the loss term. Of course, we add a degradation term because, of course, when you have a system, of course, you imagine of sometimes that it can happen a degradation here, that tau naught is the degradation term. And here we have like the diffusion term. Of course, we allow oligomers to diffuse because oligomer will diffuse and go at the neighborhood of the neuron and send them cytotoxic signal, right? So here, this is the equation for free oligomers. When we finish with the equation of free oligomers, here we take the equation for oligomers in the plaque. That means the equation that are always here in the plaque. Of course, there is nothing for this kind of equation because it is just the displacement of this in the plaque. And this displacement, of course, is just through the recruitment term. What I lose in the here, what I lose here in the equation for free oligomers, I will gain it here in the equation of oligomer in the plaque. So, of course, here we add also a degradation because we assume that there is a process in the brain that can allow the degradation of a part of oligomer that are in the plaque, right? Of course. So this is the equation for oligomers. Of course, we do the same for the other equations. And the other one is the equation for monomers. Monomers, that mean here, the element that are produced by the neuron after cleavage. So for the monomers, A beta monomers, it is just a balanced equation. That means we see what we lose. Of course, here, two monomers can merge or can aggregate to form a proto-oligomers of size 2. That's why here we have this loss term, which is when two monomers stick together. So here we have a loss term due to the fact that when a proto-oligomers of size I gain a monomer, because it is all the proto-oligomers who can gain monomer, that's why we have all the sum. And the size max of proto-oligomers is I0 minus 1. So we do the sum from 2 to I0. This is the rate of gain of monomer from proto-oligomers. So this is lost by the population of monomers. Of course, all the proto-oligomers can lose one monomer. So this is also with the rate B multiplied by the sum of all this, which will be the gain of monomer. So this is also a gain term. This gain term, of course, when I said before, when we have the activation of microglia cells, these microglia cells, of course, activate an inflammatory process, and we have the production of interleukins. So the production of interleukins depend on the on the presence of oligomer, because when there are oligomers, we have activation of microglia, and so microglia can produce interleukin. That's why here we have a gain term depending on U and I. Now this is a gain term of monomer depending on U and R through the function S, and the function S is just this function here, right? So we have also a degradation rate. That means a degradation rate of monomers here. We imagine that, of course, it could be degraded in the brain. So we allow also the monomer to diffuse in the considered domain. That's why we have the diffusion term here, right? This is the equation for monomers. So for the microglia cells, of course, the microglia cells, as I said, their role is, of course, to identify where there is a lot of oligomers. And when they see a lot of oligomers, they have to take them and displace them in a plaque. So, of course, there is a diffusion, an oriented diffusion, because, of course, they don't turn around like here. So they have like there is like a chemotaxis process that identify the zone or the area where there are a lot of oligomers, and so they go there and take them and put them through the plaque. So that's why in the equation of microglia cells, we have, of course, the diffusion term, which is a standard diffusion term, but we have also like this chemotaxis point, this chemotaxis term that means alpha, the divergence of m grad u, and this explains the fact that, of course, the microglia cells go directly in the zone, in the area where the concentration or the density of oligomers is huge, right? So, of course, we have the basal production of microglia cells in the brain. Of course, if there are no oligomer, or if there are oligomer, we have a basal production. All the time we have a basal production of microglia cells in the organism. Of course, this term is just a production term, and this production term, of course, depends on the presence of oligomers. And also, we cannot produce an amount of microglia cells. That's why we have the maximal capacity here. So this is the term for the production, and it is multiplied by m hat minus m, so where m hat is the maximum capacity of microglia cells in the neuron environment, right? Of course, as I said before, we also take into account the possibility that we have a degradation. So sigma is the degradation rate of microglia cells. So now it remains one equation, that means the equation for the interleukins. And the equation for the interleukins behaves as follows. For this equation, of course, we have the diffusion. We allow the interleukin to diffuse. And we have the production of interleukins. As I said before, the production of interleukins depend on the U, that means the oligomers, and it depends on microglia cells. Because if there is no oligomers, of course, there is not activation of microglia cells. So there is the process of inflammation is not at all, it not begin. So that's why here this term depend on this Michael-Menten function, depend on U, and also is multiplied by m. So also again here, tau 3 is just the degradation rate that we take into account. If there is no degradation, we will take tau 3 as equal to 0, right? So we have a general model for the scheme that we design. We note that, of course, all I said about the equation are given in 2D. in the first time, we see that, okay, we work on 2D and we add like Neumann boundary condition. So the global study, like the well-posedness of the model, the boundness of the model, of course, is in progress. It is a work in progress. However, preliminary work is done on a simplified version. So instead of working on the whole model that we are working on it, but at the beginning we say that, okay, this is the whole and the general model. What happened when we consider a simplified version of this model? To say simplified version is just a version where we have a B monomeric one. That means all the process that we have proto-oligomers of type of size 2, proto-oligomers of size 3, etc. until proto-oligomers of size I0 minus 1, we will skip this stage and take just monomers and oligomers. Okay, so monomers and oligomers, that's why we talk about B monomeric model. And this B monomeric model we take into account is here the fact that M plus M will give you. That means 2 monomers will give an oligomers. So we remove all the proto-oligomerization process. Of course, we assume the fact that, of course, when you oligomers with monomers will give oligomers also. So it do not change, which means that when a monomer meets an oligomers, the later remain oligomeric and the monomer is consumed, right? So for this new consideration, or for this new simplification, what we obtain is here, this model. And it is the first model is the model for U, that means for oligomers, like it is also the diffusion. Here it is the fact that 2 monomers can give 1 oligomers. Of course, this is the lost term when oligomers are displaced in the plaque thanks to the microglia cells, and this is just the degradation term. Of course, the equation for UP like the oligomer in the plaque, it is the same. The equation do not change. So for the equation for monomers, of course, there is no proto-oligomerization process. So for the equation for monomers, we have here the diffusion term. This is the term, the gain term that we said before, we've take into account the interleukin. So this is the degradation term. This is the term when an oligomers, of course, encounter a monomers, this with the rate R2. So this is lost by the population of monomers. And this is the case where 2 monomers match together. So it forms an oligomers. Of course, the 2 last equations are the equation for microglia and interleukin, and it is the same equation. We have here the diffusion, we have here the chemotactic place term. Here we have also the gain term of microglia cells due to the presence of oligomers, and this is nivelate, or there is a level we cannot increase the maximum size. We cannot have more than the maximum size for microglia. Here we have the DF, not DF, but the degradation term, and here it was the basal production. Of course, we have this system. For this system now, the question is, for this model, the first question we address is the behavior in homogeneous space. Okay, of course, we have this model. The behavior in homogeneous space, when you talk about homogeneous space, that means, of course, if there is no space, what do I have here? If there is no space, what do I have? So we have the following assumption. Taking gamma m depending, it is on constant like gamma naught, which means that the recruitment of oligomer to the amyloid plaque is constant. If we take the fact that the degradation term, there is no degradation, that means the degradation is negligible. So what we have to this system, we simplify, it is just a simple ordinary differential equation. And for the simple ordinary differential equation, we are able to do and to say something about the disease. This is very interesting. So in the case of Alzheimer's disease modeling, the study of the steady state is more relevant because here, of course, we talk about Alzheimer. You know that Alzheimer is linked to age. So it is the process of evolution of Alzheimer is a long process. So it's when we look to the steady state, it have a relevant. It is relevant to study the steady state of this model too. So when we look to the stationary point of this model, we see that, of course, we have to solve this system. And to solve this system, of course, it is easy to see that the disease-free equilibriums, that mean the system without disease, the disease-free equilibrium is when we have this point is 0, 0, 0 here, lambda m over sigma here 0. This is the disease-free equilibrium. Of course, when we look to this disease-free equilibrium, the question is what we can talk or say about the stability. So for this disease-free equilibrium, it is locally asymptotically stable because here, when I look to the Jacobian matrix, to the associate Jacobian matrix at this point, we can write this Jacobian matrix as this matrix like this. And for this matrix, we have nothing to do because we can see easily that, of course, the eigenvalue of this Jacobian matrix at here is minus gamma naught minus TP minus D minus sigma minus tau 3. So when we have this, beyond this disease-free equilibrium solution, there is a non-trivial equilibrium. So we have one disease-free, because here if I look to all the eigenvalue, all the eigenvalue are negative, of course. So we have the stability, the local stability. And when we want to look to another equilibrium, of course, beyond this disease equilibrium, there is a non-trivial one equilibrium solution. That means there is an endemic equilibrium solution where Alzheimer persists. So this is the question. Can I have another equilibrium point which is not a disease-free equilibrium? That means which will be an endemic equilibrium. So of course, we prove with collaborator like colleague here and Vitaly about that, we prove this theorem that, of course, all depend on the parameter. If we have this order, this inequality on the parameter sigma gamma naught 2, 3, if the product is lower than tau 1, tau s, lambda m, so for D positive small enough, we can have at least 2 positive steady states of the system. And if D is positive and large enough, then there are not positive solution of the system tree, regardless to this condition. And this is very important. And of course, to prove this, it is more or less easy. It depends on how you act. So here, the proof, I just give the sketch of the proof. We solve U and UP. The first thing is we solve U and UP because we have this system. if you have this system, you can solve U here. You can solve UP here, because we will solve U depending on M. Here UP depending on U, so we will have UP depending on M also. So that's why here we say that U is equal to here rho M square. Here UP, we give it as this, where rho is here R1 over gamma naught. So once we have this, we go to the equation of the microglia cells. For this equation, we can solve M here with this relation. That means the idea is to express all the unknown in M. So all the unknown I will express as a function of M. So that's why here we have this with here delta is this expression, sorry. Delta is this expression. So we do the same for I. That means interleukins. We have this expression. So we have a relation like a function depending on P and D, like M multiplied by P depending on M plus D is equal to M multiplied by a function F depending on M, where Pm is just this, like it is a polynomial of second degree on M, and here capital F M is this expression. So all the work is now how to solve this equation. Of course, if M is not vanishing, we can say that Pm plus D is equal to Fm. So that's why here we remark that M equal to 0, it is exactly this is free equilibrium. And we always know that this is free equilibrium is locally stable. So we have to determine the value when M is not equal to 0, determine the value where Pm plus D is equal to Fm. And so to do that, the thing is the same. Like you will look what happened at 0 and what happened at M. So what happened at 0 we know, what happened at M we know, and when we look to the limit, we can see that there is something that we can say when the derivative is positive or when the derivative is negative. That is all the game here. So when we do that, of course, you can believe me. So we have, of course, the result that, of course, we can have Pm lower than Fm for M in this 0M naught and Pm equal exactly of Fm naught, right? So, of course, we continue the same game to identify the maximum that we can have when we take the difference between F and P. So to do that, you can, of course, put d tilde as the difference from y naught. Of course, we can take the inequality that we have and say that, of course, we have the existence of positive solution of this. Okay, this is exactly what you know about the Rolle theorem. Okay, or like the TV, like theorem of intermediate value, right? So all the sketch is here. And when we do that, okay, we prove our famous theorem. This is the theorem that we have, the fact that, of course, when we have this inequality, we can have positive steady state. Okay. So what happened once we do that? We want now to illustrate this. We want to illustrate this like in numerical point of view. So before that, let me just show you the table that we have, the table of numerical simulation that we take here, and all the values are identified, of course, on existing value on in the literature and sometimes it is just, we have just approximatively the existing value because there are not all the study to identify exactly the parameter. So R0 here, it describes the B monomeric polynomial rate, etc. We have all the parameter here and all their value and all the units, corresponding units, okay, for the degradation, etc. For this parameter, okay, we want to see what happened here. So that means we want to identify the disease-free equilibrium and the two other positive equilibrium. Okay, so we analyze the bifurcation diagram. To do that, of course, the better thing to do is to analyze the bifurcation diagram for the concentration of interleukins at the equilibrium. Depending on the degradation rate, of course, of monomers, D as the bifurcation parameter. So here we see that when we compute the inflammation here and the degradation rate D, we have obtained this bifurcation diagram of the steady state of the concentration of interleukins I star in terms of degradation rate of monomers D. The disease-free equilibrium exists. We see that the disease-free equilibrium exists for all D greater than D. For all D positive, here we have a disease-free equilibrium, and here when D is here lower than DC, when D is lower than DC, we have two non-trivial equilibrium, of course, where the maximum one is stable. We have this 2-1. The maximal one is stable, and this one is unstable. Okay, so this confirms the fact that, of course, the theoretical study is correct. We are able to identify two positive equilibrium. Okay, so we observe this in these figures. We observe in the bifurcation diagram that for D positive, the disease-free equilibrium is also asymptotically stable. Moreover, there is a critical, this is the critical value here. It is the critical value for the degradation rate, and it is almost of around 0.4, which we call the critical degradation rate of persistency, such that for D lower than DC, there is two positive equilibrium steady state, where the maximum one is asymptotically stable and the other one is linearly unstable. And when D is greater than DC, when I'm here, we have only the disease-free equilibrium, okay, of the system. So, of course, we do for the inflammation here, when we take initial data for numerical simulation of homogeneous model, we take U0 as equal the concentration, the initial concentration of oligomer. Here we take all the initial concentration as here. What we obtain for the distribution is that here, when we plot here inflammation and degradation, we see that, of course, asymptotic behavior of solution in terms of degradation rate of monomer D, we say that, of course, when we are in this region, we have the persistency of the disease, and this is like the attraction basin. That means when we are here in this zone, there is nothing. We are disease-free equilibrium. When we are here at the left of the right of DC, there is nothing happened. So we have just the disease-free equilibrium. So there is no disease here. Of course, when our value D is lower than DC, here in this part, we have no disease. And here we have the persistence of the disease. So in the previous figures, we observe the phenomenon of hysteresis. This is the phenomenon of hysteresis for D lower than DC, where DC is what we call before the critical degradation rate, which implies the existence of a critical threshold. So there is a critical threshold for the inflammation. So that means for this inflammation, if I'm here, it persists, and if I'm here, the disease do not persist at all. Okay, this shows that, of course, the inflammation is important to take into account when you are modeling Alzheimer's disease. Moreover, for small value of D, a small initial condition of interleukin I0 is sufficient. It is sufficient for the persistence of the disease, while for the value close to critical degradation rate of persistency DC, a high initial concentration is needed, of course, right? So this was one of the first figure that we show. So here, of course, again, we can plot in the same diagram, we can plot the concentration here, all the concentration. That means in U we have blue, here UP, M, capital M, and I. So this is all the concentration that we plot here, and just at right, we have also the same thing where we plot depending on the critical IC, we plot the zone that we have disease-free or persistency of the disease. So here we see that at the right, because the figure at the left is just the solution of the homogeneous system when D is exactly equal to 0.15. And here, I0 is 0.15 also mole per liter. And in the right, we have the asymptotic behavior in terms of D and I0. So also, the figures show that if I fix I0 not very big, that means here 0.15 here, we observe that the solution converges to the disease-free equilibrium. And we see that here, in the concentration, all decrease toward the disease-free equilibrium. In this example, the concentration of interleukin is decreasing and the threshold of inflammation is not reached. So moreover, the concentration of monomer increase until it reached the maximum value. So we have here this value, this value for I0. So if I0 is here, we see it is here. If I see this line, above this line, we have also the persistency of the disease, and above we have just, and below, sorry, we have just the disease-free equilibrium here, right? So that means the initial concentration of interleukin also play a role in the persistency or not of the disease. So of course, we can compute again now when we increase the concentration of I0, that means the initial concentration of interleukin, we see here that, of course, the dynamic change because all do not decrease towards zero. Here we have all the concentration. The concentration are not decreasing towards zero. And so that means when my I0 is here, is above this red line, we see that, of course, we have also persistency here, and we have, of course, disease-free equilibrium here, but we see that we do not converge toward the disease-free equilibrium, of course. So if we increase the value of initial inflammation here, I0 to 0.4, the solution converges to the stable positive steady state. So since the critical threshold IC is less than I0. Here, the free oligomers in the amyloid plaque are increasing toward. So we have just all are increasing here, the corresponding value. So the inflammation is initially decreasing until it reaches the minimum value and eventually increase toward an equilibrium value. And here we see that the concentration of monomer here is increasing and decreasing phase. There is two phases, an increasing phase and an decreasing phase, because the monomer is here. This is, we have an increasing phase here, and also it decreases and becomes stable, right? So that's mean just to show you that, of course, we have a lot of dynamics, and it depends how you choose your initial concentration for the interleukins and how is the parameter, the relation of order that we see when DC, sigma, tau 3, etc. If we have the condition of our theorem, so we are able to show as theoretically and numerically that we have, of course, the existence of order critical point, different from the disease free equilibrium. Of course, we can continue again here. Here again, we increase the value of D, and we increase again the value of I0. If we increase again the value of I0 here, we see that, of course, and here it is the value of D. Here also, we see that the dynamic change, because all decrease at the beginning, we have the increase, but after that, all decrease towards 0. And we have that, of course, we have also disease, the persistence of the disease here, and here we have free disease here. So as I said before, if we increase again I0 to 0.8 mole per liter, we observe that the solution converges to the free disease equilibrium. In this example, the concentration of interleukin is eventually decreasing. So the concentration is eventually decreasing since the threshold of inflammation is not reached. So moreover, the concentration of monomer, free oligomer, and oligomer in the amyloid plaque increase until they reach also their corresponding maximum value. So that means you see that the inflammation is very important if we want to keep free or persistency of the disease in our model. So also we do another test here, another test to increase again I0. Here also we increase again I0. That means we are here now in the persistency, and you see that the dynamic change totally, the dynamic change, we do not converge toward the disease-free equilibrium, but we converge toward a positive equilibrium. That means we will have the persistency of the disease. So that's I say here, if we, of course, increase again the I0, the solution converge towards the positive, stable, steady state, leading to the persistency of Alzheimer, since the critical threshold IC is less than I0. And if it is less than I0, so we come to disease-free equilibrium. So the concentration of free oligomers and oligomers in amyloid plaque, if I see here, this dynamic, are increasing toward the corresponding value of equilibrium. So initially, the inflammation decreased until it reached the minimum value and eventually increase again, right? And this is very important to highlight what we do in this study. So, of course, here, of course, we do the maximal thing. That means we take I naught very, very big, like 2 mole per liter, if we take it here, we see that, of course, we converge toward the disease-free equilibrium if we look to this diagram. So that's mean the choice of the initial concentration of interleukin is very important if you want to say something about the dynamic of the persistency or not of our disease, of the Alzheimer's disease. So, of course, we can investigate the effect of monomer concentration. Why not? That means here we take all initial concentration as known and we make variable the initial concentration of monomer. So we are looking the dependency of the dynamic to the initial concentration of monomers. And if you look to that, we see that, of course, here we have also the diagram is the same. We have also the persistency part, but here it is depending not on I naught, it depends now on MC. On monomer, a critical value of monomer. So here, this is the critical value of monomers. This is also DC, the critical value of the degradation rate. And we see that we have also persistency zone and area and free disease area right here. So we observe the same phenomenon of hysteresis when D is lower of DC. We have the same hysteresis here where DC is the critical degradation as we said before. So MC, that means the critical value of M positive determine if Alzheimer persists or not. So also we can investigate the persistency or not of Alzheimer disease, okay, when we have to choose the minimal concentration of monomers, right? So what we have here as a conclusion is that for degradation rate of monomers satisfied D lower than DC, solution of homogeneous model converge to disease-free equilibrium when M is lower than MC, and it converges to disease-free equilibrium when M naught is greater than MC. Okay. So, of course, when we look to the same, so when we in here, we take M naught is equal to 0.7 and D is the critical degradation rate. Here we see that the solution converge toward the disease-free equilibrium, and the bifurcation diagram, if you look at the bifurcation diagram here, we see also here we have the critical value of on the initial condition. When we are above this critical value, we see that we can have persistency also of the disease. And if you are below to this critical line, we have the disease-free equilibrium. So that means the disease, Alzheimer's disease, do not persist here in this term. So the observation is that the solution converges toward the disease-free equilibrium. In this example, the concentration of monomer is decreasing, of course, contrary to what we have for the interleukin, due to its intersect degradation, because we have the degradation and the formation of free oligomer. Moreover, the concentration of free oligomers and amyloid plaque and interleukin increase until they reach their maximum like this, and they decrease again toward 0, right? And when we increase again the value of M naught, going from 0.7 to 1, with the same value of D, critical value D, we obtain, with the same value of D, we obtain a different diagram. the different diagram, that means when we look to the dynamic of the concentration, we do not converge toward the disease-free toward zero. That means we have another dynamic. That's mean here, if you look to the bifurcation diagram, we see that we are here, so the disease will persist. Of course, here we have free disease equilibrium. And the same thing is, the conclusion is that we observe that the solution converges to the positive, stable, steady state. Since the critical threshold MC here is less than M naught. If MC is less than M naught, and if M naught is here, when we are here in all this zone, we have the persistency of the disease. Of course, when we look to this dynamic, we see that the free oligomers, the amyloid plaque, and interleukins are increasing toward the corresponding value of equilibrium. So the monomer is initially decreasing until it reaches its minimum value, and eventually it increases again toward the equilibrium value. So the general conclusion that we have is just, even if we work in a very simplified model, that means the model where we do not take into account the proto-oligomerization process, we observe very big and very helpful dynamics on the disease-free equilibrium or not. And it can depend on the inflammatory process, and it can depend also on the choice of the initial condition of monomers. So for this simplified model, it allows us to get the first qualitative approach in understanding the influence of inflammation and degradation rate in the persistency of Alzheimer through a phenomenon of hysteresis. So this qualitative analysis suggests that Alzheimer's may be triggered by an initial high concentration of interleukins in its progression, and its progression could be mitigated in an efficacious anti-inflammatory treatment would be applied in an early stage of the disease. So there is a work in this size, I don't know to say, there is a work in this point of view, and it is the work of Imbibo, who suggests that, of course, we can use treatment with something like the NSAID. We use this NSAID, it is like an anti-inflammatory treatment that can help for cognitive impairment. But for this moment, I didn't see a very experimental work to highlight all this. So furthermore, an interesting approach might be the study of effective time of applying anti-inflammatory dose in order to complement the stress mechanism given by the UPR, because we do not take into account the UPR in lowering the production of Aβ-monomers and not interfering with microglia activation cycle that counteract the excess of toxic amyloid. So this is what we obtained for this time. And of course, the work for the huge model where we have chemotaxi, where we have all the big stuff, the work is on is going on, and we hope to find nice result. As we see here, with this very simple model, we are able to see something about the effect of inflammatory process in the Alzheimer's disease. So I finished my talk. I hope it was interesting for you.
Yes, thank you very much, Leon, for this really interesting talk. It was, I'm sure, it was interesting for everybody. We are a little bit late, but I hope that we still have some time for discussion. Do you have some time, Leon?
Yes.
Okay, because we have already a question from the audience. Please, Alexander Prishepov, you can ask your question.
Yeah, I have a question. Does this model have analogs? There are other models that describe this disease.
Yes, for this, there are other models that describe this disease, but all the models that we see for this moment, a lot of this model do not take account the inflammatory process. So the model that we see, all the work that we see is that, of course, just you want to model, okay, like the external lesion or internal lesion. So you focus on this and you do your model, you analyze the existence of model, you do some numerical, etc., etc. And here what we add more is just, of course, there is an inflammatory process and we wanted to know the effect of this inflammatory process on the dynamic. So in my knowledge, I didn't for this time see a general model where the dynamics and the effect of inflammation is taken into account. But probably it exists, but we didn't see it yet.
Okay, thank you.
You're welcome.
Yes, there is, excuse me, another question. Елизавета Almazova, please.
I wanted to ask, could you please return to the slide number 19?
Okay.
It just was that moment when I was a bit confused. It was said that we are acting in the dimension. We have either 2 dimensions or 3 dimensions. D is equal to 2 and 3. And when do we use when? How is it distinguished?
To distinguish the dimension?
Yeah.
Yes. Here what we say is just, of course, it is a very simplified for the brain. That's mean. I don't know if you see the table here.
Yeah, we see this.
Yeah. So what we say that it is a very simplification. Like we say that, okay, this is our brain. We say our brain like something like this, and of course you have neuron something like you have neuron here, you have all your proto-oligomers, your oligomers here, your oligomers can form proto-oligomers, etc. This is a very simplified modelization because we are not for this time able to say that, okay, we take a very real form or a very real area for the brain. So the brain is something like in a 3D. In 3D, and for this moment, we want to know what happened if you are in a simplified version in 2D, how to do. But we are not, for this time, we are not able to say something if you go in 3D.
Yes, and I can also complete this answer. In fact, the study presented today by Leon, it doesn't take into account the space variable, right? So what we saw today, there is no space variable, neither 2D nor 3D. It was without space variable. The model which you presented in the beginning, there was indeed the space variable, and then you consider this ordinary differential system of equations. What is the difference? So what new information, if we introduce the space variable, what new information we can obtain? And the answer, well, you may answer, or I can continue my comment.
You can.
The space variable here is very important because when we study plaque formation, it is determined by the spatial distribution of these monomers and oligomers. So space variable is important. 2-dimension or 3-dimension, it is less important because we talk basically about qualitative results So the difference between 2D and 3D, it can give some difference in numbers, in quantitative result, but from the qualitative point of view, I think that these two cases are quite close to each other. Okay. Yes. So I also have a couple of questions or comments in spite of the fact this is our joint work, but each time I learn something new. So Leon, could you please go to slide number 7?
Yes.
Yeah, this is something which maybe I did not understand exactly. So when you say that there are 95% of cases, well, we can say of normal cleavage, and
Yes.
5% of this abnormal cleavage. So do you mean all people, I mean even healthy people, which can have this abnormal cleavage, or what? Or this concerns already people who have Alzheimer's disease? This 5%.
Yes, this 5% is just this. I think this data are obtained with the people who have Alzheimer's disease.
Okay, so when we take to make it sure for myself and for other listeners, so if we take a person who already developed Alzheimer's disease, so in 95% of cases this protein is normal, and in 5 we can say 5% or of these proteins are abnormal, meaning that their size, because the difference between the two is the size of these proteins. In 5%, they are abnormal, and these are this 5% which lead to the aggregation of these oligomers and to the cytotoxic effects of this aggregation. So all that already for people who have Alzheimer's disease, right?
Right.
Yes. So
Yes.
the next question, yes, and of course it was largely discussed, but I think it might be useful to repeat.
Yes.
So this beta amyloids, this 5% which are bad. Why do they appear? So if we have a healthy person, at least a person for whom there is no manifestation of Alzheimer's disease. So, as you say, in this case, there are no beta amyloid, no this 5%. So, how these beta amyloids appear? What is the reason for their appearance?
Yes, this is statistic for people who develop, but for people who do not develop, of course, for a reason that is not unknown, which is unknown for this moment, of course, the beta secretase can act at the place of alpha secretase, but there is no percentage of given percentage. It is perhaps very lower than 1%, but it happier. That's why the biologists and the biology and the medicine is not for this time able to explain why beta secretase act at the place of alpha secretase. This is very dilemma. That means if we know why, this is the beginning point of helping people who are ill from Alzheimer.
So we don't know now. I mean,
no,
medical doctors, researchers don't know now how this beta secretase appear. Or
yes.
If you take a healthy person, does he have this beta secretase already, or
yes?
So everybody has, even
everybody
healthy.
Have that.
Everybody has this beta secretase, even healthy people, but probably the percentage of this beta secretase is less for healthy people, right?
Yes.
And then something happened, we don't know what. The percentage of this beta secretase increases.
Yes.
And this finally can initiate this Alzheimer's disease. Yeah,
it's exactly that.
So maybe, well, maybe, and I suppose that this is also discussed in the medical literature. Maybe the reason for that, these are some mutations.
So wait, probably there is some mutations
Which lead to larger production of beta secretase, right?
Yes, and I think there is a lack of study on this side to investigate why alpha secretase, of course, which have another role, come and play the role of beta secretase, come and play the role of alpha secretase. This is the very dilemma. We don't know.
Right.
We don't know.
But
there is some mutation.
Yes, it's a
behind.
Yeah, it's a plausible hypothesis. And moreover, when we say that Alzheimer's disease emerges for older people, so this can be also related. Why for older people? Because there are more time to develop these mutations.
Yes, it takes more time, Wes.
So this is why, well, of course, it's a hypothesis. We don't have yet confirmation, but the hypothesis is that why for all the people? Because there are more time to develop these mutations, and these mutations lead to the to larger production of beta secretase.
Beta secretase. So the beta secretase.
Yes. Yeah. At this point, so when there are mutations, production of beta secretase, production of beta amyloids, then, and as you explained, it is a necessary condition for the disease development, but it is not yet sufficient because we need some additional factor to initiate the disease. Even when we have this beta secretase, but we need something more, and in particular, it can be inflammation, right?
Yes.
So just to trigger the disease, to initiate the disease, because as you showed, if there is some inflammation which can be related to some other factors, something happens.
Yes.
The person has inflammation. This inflammation may not be necessarily in the brain. It can be anywhere in the body.
Yes.
But with blood flow, these inflammatory cytokines, they are brought to the brain.
Yes.
And there in the brain, this inflammation, as you explained, can trigger can initiate this larger production of beta amyloids, the aggregation, and all the cytotoxic effects. This is very important. Of course, not all of this is confirmed, but this hypothesis look quite plausible. Yes. And my additional comment or question, and I think this is also very interesting, is related to anti-inflammatory treatment. So, because in the model you presented, inflammation acts to promote the disease. So, okay, larger inflammation, more chances to initiate the disease.
Yes.
But on the other hand, we know that inflammation is a very complex process and it has different roles in the body. In particular, inflammation promotes immune response. So this microglial cells, it's a variant of macrophages. It's something which is similar to macrophages. These are immune cells. So the question is, and this you did not take into account in the model, whether inflammatory cytokines can promote production or influx of microglial cells. And microglial cells, they act also to remove this proto-oligomers and oligomers. You see, so there are different actions. One of them, different actions of inflammation, possibly. One of them acts to promote the disease, Alzheimer's disease, and another one may be through the immune response to downregulate, to decrease the development of the Alzheimer's disease. So I suggest to think about that and to discuss this question, of course, not now, but later in more detail, because you referred to the work in the literature, and I think this question was studied and maybe studied till now about the influence of anti-inflammatory treatment, right, on the Alzheimer's disease. If we say that inflammation acts to promote the Alzheimer's disease, then the logical conclusion is, okay, let us give anti-inflammatory treatment and then we will stop the disease. But the data do not confirm that. This is the problem. The data do not confirm. Why? We don't know, but maybe because decreasing inflammation will also decrease positive action of inflammation through the immune response. So I think that this is a very interesting question to discuss and to put in the model these different actions of inflammation.
Okay, thank you very much. I will for sure look for this in the literature and of course how to incorporate inflammation, anti-inflammation treatment.
Yeah, because if we talk about not Alzheimer's disease, but different, but other diseases, we can say about whatever viral infection, atherosclerosis, and other diseases. We know that there are two types of macrophages. Here it's microglial cells, but they are similar to macrophages. That there are different types of macrophages: pro-inflammatory, anti-inflammatory. We know that inflammation plays this important role in the immune response, which is really very, very important as a part of the immune response of our organism to different diseases. So I think that we can go more profoundly in the analysis of the role of inflammation in the Alzheimer's disease. And by the way, we have some people here, even in the audience, who work on who study the role of inflammation in different diseases, so we can discuss these questions.
For sure. Thank you very much for this comment.
Okay, Leon, thanks a lot. I think that we don't have other questions, so I thank you again for this very interesting presentation and of course very, very important topic. Thanks again. Thanks to all our listeners. We finished our seminar today. Have a good day, everybody, and goodbye for now.
Okay, thank you very much to you. Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you. Goodbye.
Goodbye. Thank you.